Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I'm Arif and I welcome you all in today's session. To access the notebook for today's session, you can access course page on my personal website arifbut.me. The other way is to download all the notebook files from course GitHub account ArifPUCAT, and all the notebooks for this course are housed in this public data science repository. Well, this is the Jupyter Notebook dashboard running locally on my machine at port 8888. And here is the notebook for lecture number 6.10 of the 6th module, overview of machine learning for the course titled Tools and Techniques for Data Science. Well, I think this is our 4th session on data pre-processing and feature engineering. We are done with handling outliers, missing value imputation, and encoding categorical features. And today we will discuss feature scaling. So let me move ahead and see the agenda of today's session. As usual, we will start with a quick recap of data pre-processing and feature engineering. We will have a detailed theoretical discussion on what is feature scaling, why do we need to scale our data, and how to perform feature scaling. Then we will use NumPy and scikit-learn to practically perform the 4 famous scaling techniques on our toy dataset. The MaxAbsScalar, MinMaxScalar, Standard and RobustScalar. We will also visualize the data before and after scaling for better visualization and understanding of the concepts. We will also check or verify that the distribution of the data should not change after scaling. And finally, at the very end, we will take a classification dataset and will perform scaling on its numerical feature columns after, of course, doing our train test split. We have a lot to do and a lot to learn today. So let's start playing. My dear students, as I said many a time before as well, that a teacher is someone who always repeat. So let me describe the data pre-processing and feature engineering again. Data pre-processing is the process of making your data ready to be fed to the machine learning model, while this feature engineering is the process of using domain knowledge to extract features from raw data using data mining techniques. And these are the 6 tasks that we normally perform in this phase. And we are done with the first 3, that is detecting and handling outliers, missing values imputation, and encoding of categorical features. Today we will discuss and practically understand different techniques for feature scaling. Okay, so let us start with the theoretical concepts behind feature scaling by answering the what, why, and how questions. And first of all, what is feature scaling? My dear students, a feature scaling is the process of transforming numeric columns to a common scale. A dataset may contain different types of variables having different magnitude and units. For example, weight can be in kilogram or grams, age can be in years or maybe months, salary can be in thousands or maybe lakh, and so on. So they might differ in terms of range of values. For example, a machine learning model might consider a value of 3000 grams to be greater than 5 kilogram. And of course, the units will not be there inside your values of the columns. So 3000 will be, of course, greater than 5, while it is not correct. Anyway, consider this dataset having age in years and salary in Pak rupees. This salary variable having large range of values will, of course, dominate the age variable. And the goal of feature scaling is to make sure that features are almost on the same scale, so that each feature plays an equally important role for the machine learning model. So before feeding our data to a machine learning model, we may have to apply feature scaling on real valued input as well as on the output variables. Well, this image shows the normalization and standardization, which are two techniques that are used during data pre-processing to adjust the features to a common scale. This normalization is rescaling of the data from original range so that all values are within the range of 0 and 1 as shown over here in this upper graph. This standardization is rescaling of the data from original range so that all the values are centered around mean with a standard deviation of 1. And this is shown in this lower graph. Note that this time the values are not restricted to a particular range. However, we can say that majority of the values will be ranging from -1 to +1. Another important point to keep in mind is that after scaling, the distribution of the data must not change. A natural question that might come to your mind is that whether we should use this normalization technique or this standardization technique in order to scale your data. Well, remember, as a thumb rule, use standardization if your data is normally distributed, otherwise use normalization. Moreover, this standardization technique is more robust to scalar, rather more robust to outliers, and soon we will practically see this. Anyway, my dear students, after understanding or answering the what part of the question, let's move on to the why part. That is, why do we need to scale our data? I think I have partially answered it, but let's dig a little deeper. Many machine learning algorithms perform better or they converge faster when features are on a relatively similar scale and close to normally distributed. My dear students, all distance-based algorithms like k-nearest neighbors, k-means and support vector machine are most affected by the range of features. This is because behind the scene, they are using distances between data points to determine their similarity. And this is shown in this screenshot as well, where I have calculated the Euclidean distance between, let's suppose this person 1 and person 2 over here. You know what is Euclidean distance. So I've calculated the Euclidean distance between person 1 and person 2, which comes out to be 26,000, while the Euclidean distance between person 2 and person 3 comes out to be 6,000. Sorry for this typo over here. The spelling of Euclidean is Euclidean, not this. Sorry for this. So if the task is to identify the nearest neighbor of, let's suppose, person 2 from person 1 and person 3, we can say that this person 3 is more close to person 2 because this person 2 and person 3 has quite a less distance, that is 6,000. So person 2 is more close to person 3 as compared to person 1. I hope this is making sense. Of course, we will once again dig down deeper once we will be studying the k-nearest neighbor or other distance-based machine learning algorithms. For the time being, just remember this is the Euclidean formula and we calculate the Euclidean distance between every observation of our dataset. Anyway, the idea behind feature scaling is that if you want to do a comparison between two entities, we should bring them on the same scale. Well, my dear students, like distance-based algorithms, this gradient distance-based algorithm like linear regression, logistic regression, and neural networks as well, they also require data to be scaled. This is because the difference in ranges of features will cause different step size for each feature in case of gradient descent-based algorithms. So to ensure that gradient descent moves smoothly towards the minima and that the steps for gradient descent are updated at the same rate for all features, we of course need to scale the data inside all the columns before feeding it to the model. Therefore, remember, for all distance-based and gradient descent-based machine learning algorithms, you need to scale your data. However, there are certain algorithms like naive Bayes, uh, uh, this LDA, linear discriminant analysis, and tree-based models like decision tree, random forest, and gradient boosting. These are the algorithms where scaling or no scaling makes no difference. Okay, so we are done with the why part of the question, and now we have a fair idea as to what all machine learning algorithms require us to scale the numerical features of our dataset, and what are the reasons to scale or not to scale. Now it is time to move on to the third question, and that is how to perform feature scaling. Once again, consider the same toy dataset having two input features, age and salary, whose units are years and parked rupees respectively. If the data of a column is normally distributed, we do standardization, which is also known as z-score normalization. Well, this calculation is quite simple. We just subtract every value from mean and then divide it by the standard deviation. So in standardization, features are scaled to have 0 mean and 1 standard deviation. And this lower table contains the standardized age and salary columns. Of course, if you calculate the mean and standard deviation of these transformed columns, they will be 0 and 1 respectively. Similarly, my dear students, if the data of your column is not normally distributed, we do normalization, which is also known as min-max normalization. The calculation is once again very simple. We just subtract the minimum from each data point and then divide it by the difference of maximum and minimum, that is the range. So in min-max scaling, features are scaled in the range of 0 and 1. And this upper table contains the normalized dataset using MinMaxScalar. My dear students, a major limitation, of course, of MinMaxScalar is that it is affected by outliers, as it is apparent from the formula. Okay, so the pre-processing module of scikit-learn library provides a lot of transformers for feature scaling, and in today's session we will practically understand and implement these four: the MaxAbsScalar, MinMaxScalar, RobustScalar, and StandardScalar. And this StandardScalar is actually the industry's go-to algorithm that is used for feature scaling. Okay, so far so good. I think enough of theoretical discussion on scaling of data. Let's do this practically on our toy dataset. This code cell is actually, this code cell is actually creating a sample data frame having just two feature columns using our dictionary. So we have two hypothetical features, F1 and F2, and the dataset has just 4 observations. Let me call the describe method of this to check out the mean, standard deviation, min, max, 25th, 50th, and 75th percentiles of the feature column. Remember, my dear students, this 25th percentile is the first quartile or Q1. This 50th percentile is the second quartile or Q2, or also known as the median. And this 75th percentile is the third quartile or Q3. Okay, fine. Now let us quickly apply different scaling techniques on these two features of our data set. And we will do this using NumPy by doing all the calculations manually, as well as using appropriate scikit-learn transformer classes for scaling. We will also visualize the data using scatter plot before and after applying each technique for better understanding. And finally, we will also check the distribution of our data before and after scaling. So this is what we need to do for all these different scaling techniques. Fine. Excuse me. Let's start with MaxAbsScalar. And from the formula of MaxAbsScalar, we simply divide each data value by the by the absolute maximum. Uh, of course, it does not shift or center the data as and this does not, of course, destroy any sparsity. Yes, I'm sorry for this pronunciation. Of course, this MaxAbsScalar suffers from the presence of outliers in your dataset. So if we have a outlier, so it will be affected by that. Well, anyway, this code cell over here is actually using list comprehension to create two lists. Let me highlight this. So this is list comprehension. This first, which I have highlighted, is actually for the scaled values of F1 column of the data frame, and this second one is using the same formula for the scaled values of F2 columns of the data frame. Note that we are dividing each data value of a column with the absolute maximum. Finally, I am creating a new data frame, df1 from the two lists using a dictionary having key as the column name and values as the corresponding lists. Let me execute this. I hope this is making sense. So these are the scaled values of this data frame. You see, let me just show you over here. So this is the original data frame, and this is the scaled data frame after performing MaxAbsScalar using this formula using NumPy. Great. Anyway, so this over here, this code cell now will do the same using the MaxAbsScalar transformer of sklearn. We simply create the instance and then we call fit transform on the MaxAbsScalar object by passing it both the columns of the data frame. Rather, over here we are passing it the entire data frame. It will return us a NumPy array of scaled values, of course, of size 4 by 2. And finally, I am converting the NumPy array to data frame df2 this time for better visualization and comparing it with the df1. You see, this is df1 that we have computed using NumPy, and this is df2 that we have computed using the MaxAbsScalar transformer of sklearn preprocessing module. Exactly same. Great. Well, this code cell now is actually drawing a scatter plot between feature 1 and feature 2. Note actually these two lines, just these two lines. This first line is plotting the 4 points of column F1 along x-axis and column F2 along y-axis. I'm using the data frame DF. I'm using the data frame DF, that is the original data frame, which contains data before scaling. I've used 4 different colors for each data point, and the marker is star. And the second line below it is plotting the 4 points of F1 along x-axis and F2 along y-axis. Note that here I'm using the data frame DF2, which contains data after scaling. The markers I have used are circles for these scaled data points. I hope the rest of the code is simple. Let me just execute it. Great. Note these 4 stars, 1, 2, 3, 4. They represent the data points before scaling, and these 4 circles represent the data points after scaling. This blue star represents F1 equals almost 12 and F2 almost equals 2, and its corresponding scaled data point is this blue circle with a scaled value of F1 almost 0.6 and F2 almost 0.4 or 0.5. You can check this out over here, 0.66 and 0.4. So this is the blue point. Please spend some time and understand how these original data points have been shrinked within this range and scaled as well. And let me move on to the next scaling technique, and that is the min-max scaling. Well, the calculation of min-max scalar is also simple. We simply subtract the minimum from each data point and then divide by the difference of maximum and minimum as shown in this formula over here. This is also known as min-max normalization and is used when the data of a column is not normally distributed. It scales and translates the feature values which such that they fall in the range of 0 and 1. And if, of course, if there are negative values under your column, it shrinks the data within the range of -1 to +1. Okay, let me describe this formula a little bit more. Remember, if xi is minimum, the numerator will become 0. Hence, this xi bar will be 0. Similarly, if xi is maximum, the numerator will be equal to the denominator. Therefore, this xi bar will be 1. And finally, if the value of xi is between the minimum and maximum value, then this xi bar will be between 0 and 1. I hope this makes sense. Finally, this min-max scalar responds well if the standard deviation is small and when distribution is not Gaussian. And of course, it is sensitive to outliers. Let me display the contents of our toy dataset, again having 2 input features and 4 rows. And this code cell over here is actually once again using list comprehension and NumPy's min-max methods on the 2 columns to create 2 lists. And finally, I'm generating a data frame df1 from the 2 lists using a dictionary having key as the column name and value as the corresponding list. Let me execute this. Note that under column F1, the maximum value before scaling was 18, this one. And over here it is 1. And the minimum value before scaling under F1 was this 10. And after scaling it is 0. This is what I said while describing the formula. Anyway, let's do it using the MinMaxScalar transformer of preprocessing module of sklearn. We have imported it. We have created the instance. Then we have called fit transform method and passed it the entire data frame. It will return a NumPy array of scaled values. And in the last line over here, I just converted the NumPy array to data frame df2 for better visualization. Let me just execute it. Great. Note both this df1 and this df2 have same scaled values, whether we have used NumPy or we have used MinMaxScalar. Of course, on large data sets, we will go with these transformers of sklearn. Finally, here is once again the code that is used to visualize the data before and after scaling. Let me just execute it. This is the same code, just the values has been changed. Once again, the stars represent the 2D input feature vector F1 and F2 before scaling, while these circles, they represent the corresponding points after scaling. Note that all the 4 data points have been scaled and translated within the range of 0 and 1. I hope it is making sense. Let me move ahead. Here comes the StandardScalar, which is the industry's go-to algorithm. Well, this StandardScalar rescales the data from original range so that all values are centered around the mean of 0 with a standard deviation of 1. If you see this formula, we are actually calculating the z-score of each data value by subtracting it from the mean and dividing it by the standard deviation. And do note that after scaling, the values will not be restricted to a particular range, although majority around 67% will fall within one standard deviation around the mean. Let's do this using NumPy. Let me show you the data frame first. And this is the same once again code. I have used list comprehension and the mean and the STD standard deviation method of NumPy to compute it. So you see, this is the original data frame having the values given, and this is the data frame having the scaled values using this formula. Okay, so let me once again use sklearn standard scalar class. Created the instance called fit transform method. It has returned me the array, and I have used this data frame method to convert this array to a data frame for better visualization. Once again, both the data frames df1 and df2 contains scaled values using StandardScalar, and the above data frame has used NumPy, and this one has used sklearn StandardScalar transformer. And of course, here is the visualization. Once again, the same code. The two-dimensional data points, I am drawing a scatter plot for these. So these stars are the data points before StandardScalar has been applied, and these are circles are the data points representing the scaled values. Good job done. Let's move ahead and move on to the fourth one and last technique that we are going to discuss today is this robust scalar. Well, as the name suggests, this scalar is robust to outliers. My dear students, remember, if your data contains many outliers, then scaling using the mean and the standard deviation, that is StandardScalar, or even scaling using the MinMaxScalar will not work. The presence of outliers will change the probability distribution of your data when you will scale it using this StandardScalar. On the contrary, this robust scalar use quartiles or percentiles. Well, these are the two formulas. Actually, these two formulas are same. We actually subtract each data value from the second quartile, that is Q2, which is of course the median. And then we divide it by the IQR, that is interquartile range, Q3 minus Q1, which is the same as P75, that is 75th percentile minus 25th percentile. Okay, let's apply it. Here's once again the original data frame, and once again in this data cell I am using NumPy list comprehension. I'm using the quantile method of pandas series object to calculate the first, second and third quantiles, and I've used these values in the formula as discussed above. Let me execute it. Great. So we have got the scaled values of the two input feature columns. And of course, we can achieve the same using sklearn RobustScalar transformer. I hope this is piece of cake. You can compare the values of both data frames, df1 and df2, which are same. And here is the visualization of our data before and after scaling. Great, great. Well, my dear students, this screenshot actually gives a summary of the 4 scaling techniques. This leftmost table over here is the original dataset, and these remaining 4 tables contain the scaled features using this MaxAbsScalar, MinMaxScalar, StandardScalar, and RobustScalar. Well, you can also compare the 4 scatter charts, each showing the original data points as the stars, and the corresponding scaled data points as these colored circles. Please stop the screen, stop the video for some time, compare these values, have a real understanding of these 4 scaling techniques. And let me quickly show you the impact of outliers on these scaling techniques. Let me just import these libraries. Over here, I am just creating a synthetic data set. I am using this normal method of random module of NumPy. The first call to this method is creating 1000 values with a mean of 20 and standard deviation of 2. And this second call to this normal method of random module is creating 25 values with a mean of 1 and standard deviation of 2. Then I am concatenating these values to a NumPy array ARR1. So this ARR1 will contain 1025 values, 1000 values having a mean of 20, while the remaining having a mean of 1. Anyway, and once again in this line over here, I'm creating another array ARR2, but over here this time with the higher outliers. You see the mean over here is 40 and the mean over here for these 25 values is 70. And finally, I'm creating the data frame for better visualization. So this is the data frame having 1025 rows. 1000 values have been generated using this method of normal, while the remaining 25 values have been created using this value, this call to the normal. Fine. Great. So let's use the KDE plot, that is the kernel density estimate plot of CBOM, to visualize the distribution. So this is the distribution. So this is the distribution of feature 1. This is the distribution of feature 2 shown in blue. And you can see the outliers of feature 1 over here with a mean of around 1 shown in red, and the outliers of feature 2 with a mean of 70 shown in blue. These are the 25 outliers for feature 2. These are the 25 outliers for feature 1. Well, anyway, over here this code cell is using the MinMax, standard, and RobustScalar of sklearn, and creating 3 data frames from the returned NumPy arrays. So we have done this before as well. So this will just create 3 data frames, and over here I am just visualizing. I'm just plotting the distributions of the original data frames and the 3 transformed data frames. Let me just simply execute it. Great. So you can observe that the fine over here, the RobustScalar has the least impact of outliers. So you can see the distribution is not changed much over here. Fine. Great. My dear friends, I think now we have a fair idea of the what, why, and how part of the question regarding feature scaling. We have done this on a very small data set as well. We have understood the math involved behind feature scaling and have practically done all those things using NumPy as well as using scikit-learn transformers. We also have visualized the impact of scaling using the scatter plots and KDE plots. We also have seen the impact of outliers. And now I think for completeness, let me give you a quick walkthrough on a real data set of scaling its numeric columns. And for that, I'm just using a data set having 400 rows, 3 columns. The 2 input features are age and salary. Both are numeric columns. The age is in years and the salary is in Pak rupees. The output or target column is having a value of 1 or 0, specifying whether the person with that age or salary will do a purchase or not, let's suppose. So it appears to be a classification problem. Let's suppose that this is a real data set. Actually, this is not. I've just created this data set from a bigger data set just for better understanding and for keeping the things simple at the same time. Let me call describe method on this to view the mean, standard deviation, min, max, and percentiles of the age and the salary column. And let me call this info method as well. So there are no null values under any of the columns. So we are ready to go. So let's do our train test split first before we do scaling using sklearn transformer. Well, remember, this is important to avoid any data leakage. So first we call the drop method. So we have dropped the target column, and now we have the X data frame containing just the 2 input features, both numeric input features. Then we have got the target column in Pandas series named Y over here. I hope this makes sense. We have done it many times before as well. Note that both X and Y have 400 rows, and for each observation in this X, we have a corresponding output in this Y. Well, this course will import the train test split method from the from the model selection module of sklearn, and this method train test split is passed x and y. The actually the fraction of test size, which I have kept 0.2 over here, and of course the random state, which is for reproducibility. That is, every time you make this call, the same shuffling will be performed before doing a split. And this method, of course, will return a tuple containing 4 values. Each is a numpy array. Let me just execute it. Great. You see the length of the X train and Y train is 320, while the length of X test and Y test is 80. Of course, we will use the X train to train the machine learning model and the X test to evaluate the trained model. The Y train contains the target label for the training dataset, and the Y test contains the target label for the test dataset. I hope this is clear. Let me show you the shape of all these arrays. So the X train and X test, they are having two input features, F1 and F2, 320 rows for the X train and 80 rows for the X test. And of course, this Y train and Y test are just the target values. The Y train contains 320 values, while the Y test contains 80 values. Let me show you the head of these. If you see the head of X train, these are the 5 values. If you check out the head of the Y train, these are the 5 values. Do note the indices. They do map exact same shuffling for both. And similarly for the X test and Y test, the same indices. Okay, so now we have done the train test split. Let us apply a StandardScalar to the age and the salary columns. So first we create the instance of StandardScalar transformer of scikit-learn library. Then we call the fit method on age and salary column of X train. Then we call transform method on X train and X test separately, and get two arrays, X train scaled and X test scaled. Let me execute it. Note the shape of the training array is 320 rows with 2 columns, and the shape of the test array is 80 rows with 2 columns. And for better visualization, let me convert the 2 numpy arrays to data frames, and let me show you these. So this is X train scaled and this is X test scaled. Note the values of both the columns have been scaled or transformed by StandardScalar. Fine. Over here, let me call the describe method on these 2 data frames. So I've called describe method over here. Don't worry about this. This is just the round method of NumPy. If I don't call it, these will be very large values. So this is just for rounding. So this is the description of the X train scaled data frame, and this is the description of the X test scaled data frame. Note the mean of 0 and standard deviation of 1. Mean of 0 and standard deviation of 1. Over here the mean is quite close to 0, and the standard deviation is also quite close to 1. And this is because we have a smaller data set, just 80 values. Okay, finally over here, let us visualize the distribution of the 2 columns, age and salary, before and after scaling using this kernel density estimate plot of Seaborn. Over here, this is age before scaling. So this is age after scaling. This is salary before scaling and this is salary after scaling. Let me execute it. Great. You see there is no change in the distribution of the data. However, the values of both age as well as of salary has been shrinked and shifted to the mean of 0 and standard deviation of 1. So this is the distribution for the age column, the before scaling and after scaling. So you see the mean of 0, and this is the distribution for the salary column before scaling and after scaling. And after scaling you can see the mean of 0 and of course the standard deviation of 1. Well, my dear students, that is all as far as scaling of numeric input and output columns of your dataset is concerned. This is just a kickstart. There are a lot of details which we will study as they turn up once we do all these things, all these pre-processing tasks on real-world dataset in our future sessions. I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning and Allah Hafiz.